In this segment, we'll look at how large binary and textual data, generally in the megabyte size range, is stored in a database column. And we'll look at date and time column types. There's really no diagram for this, so we'll just be looking at the transcript for the background. Now, large data columns first. Databases can store media or other large pieces of binary data, and SQL provides column types for this purpose. We can declare a column that holds a binary image, say a user's photo or an MP4 recording. Such large binary data blocks are usually termed blobs for binary large object. A blob is closely related to a string. In a sense, both are sequences of bytes. But the bytes in a blob are raw data, so to speak, while those in a string have an associated character set to interpret them as symbols and a collation order by which to sort them. The distinction is small enough, however, that binary column types have many similarities to string types. So first up, binary n and var binary n. Now these MySQL types, they're not SQL standard, work almost exactly like char n and varchar n, but they're meant for raw binary data, not characters. Use binary n if you have binary data of some particular fixed length, for instance a fixed sized icon bitmap maybe. Use var binary n for variable sized binary data of some maximum length, an encrypted password perhaps. All the previously discussed trade-offs regarding storing column length, the best choice for n, disk fragmentation, and so forth for char versus varchar apply to binary n and var binary n in the same way. Now for cases where fine-grained size checking is not relevant, you don't need an exact value for n, you may use the MySQL types text for string data with character encodings or blob for raw binary data. And the data links of these column types are stored in 2 bytes, so they're very much like varchar 65535 or var binary 65535. And predictably there are variants. Tiny text, medium text, long text use 1, 3, and 4 byte lengths respectively, and so do tiny blob, medium blob, and long blob. The text and blob types are also stored differently on disk than are the varchar and var binary types. The details are a bit beyond the scope of this course, but a brief summary is that varchar and var binary are stored in a way that presumes you might want to search for patterns within the entire string or blob, and possibly randomly access strings or subportions of the data, while text and blob types assume you might search or index at most on the first few bytes of the data, and that the rest of the column data can be scattered around disk in the most storage efficient way possible, designed only for sequential retrieval and not optimized for random access within the string or binary data. For instance, if you wanted to get the last few bytes of the data easily without retrieving the entire column from disk, then varchar or var binary are better choices. And question 1 along those lines, what type would you use to store a JPEG image, do you think? And for that matter, what about an MP4 compressed video? We should actually get a different answer for each of those. If you think about it, the best choice for a JPEG data would be medium blob or maybe long blob if you anticipate really large JPEGs of over 16 million bytes or so. For the MP4, it's tougher. You don't search randomly around in a JPEG, but you might want to scrub, as they put it, back and forth in the MP4 or jump to different time offsets in it. An MP4 can easily exceed 16 megabytes, so the choice is between long blob if you don't plan to jump around in the MP4 data, or var binary and use 4 billion, the limit 4-byte storage, if you do plan to jump around. And moving on then to date and time types. MySQL and SQL offer a variety of types to record times and dates with different capabilities. The SQL standard datetime column stores a full date and time value. You use it as though it were a string when comparing and assigning values, but it's internally stored more compactly. It actually requires about 5 bytes as of the latest MySQL version. And an example of using a datetime type, I'll assume that's date of registration, as a string is right here. Now, the format for datetime values is YYYY, 4 for year, 2 for month, 2 for date with dashes, and then hours, minutes, and seconds. And the hours is in 24-hour form. Remember, the components are always in descending order of size: year, month, day, hour, minutes, seconds. In particular, do not use month, day, year. That's a uniquely American format that the rest of the world thinks is odd. The year may be just 2 digits, YYMMDD, and MySQL will cleverly decide that 70 and up are 1900s dates, while 0 through 70 are 2000s dates. And don't use this feature. And so there's question 2. Why not use this feature? To answer that, find out what infamous software problem arose about 16 years ago, as of this writing, from using 2-digit years. And if you're a college-age student, you may not remember the issue personally, but you can look it up with appropriate Google keywords. Y2K bug will work. What was the issue? Why did people use 2 digits for years in the first place? And how much did the bug cost to fix? So the answer here is that I am, probably obviously, referring to the Y2K bug, whereby millions of lines of database-related code written in the 20th century used 2-digit years, automatically assuming the 19 prefix. This worked fine up through 1999. As of 2000, years like 00 or 01 would automatically be interpreted by such software as 1900 or 1901, and 21st century credit card expiration dates and check dates, etc., would suddenly look a century old with attendant buggy behavior. Now, there were apocalyptic predictions of total financial collapse as of January 1st, 2000. As it turned out, though, so much effort was put into preemptive software repair that everything went smoothly, though a great many middle-aged COBOL programmers saw a boost to their employment prospects in the 90s, the 1990s, that is. Indeed, somewhat to the irritation of software engineers everywhere, the public assumed that the issue had been overblown because the turn-of-the-century software apocalypse was a no-show. In fact, the non-event was a testament to first-rate engineering work, and the total tab for it amounted to $300 billion in year 2000 US dollars. So why would one use 2-digit years in the first place? To save space. Yeah, disk space. When this practice started in the early 1970s, disk space cost $200 a megabyte versus the current tiny fraction of a cent. And the year 2000 was a date associated with science fiction, not the immediate financial future. So 2-digit years made sense back then. Today, there's no justification for such sloppiness. Always use 4-digit years. Now, the date type, again SQL standard, omits time information to save space in cases where time is not relevant. Birth dates, credit card expiration dates, so forth. And you can use a YYY 4-digit year, month and date format for its data. A time type, again SQL standard, omits date information for cases where only a time of day is needed, and you can use the hour, minutes, seconds format for its data. 24 hours, though, remember. Now, it does more than that. This type can represent time intervals as well, both positive and negative, as long as the absolute value of the interval is less than 840 hours, which is just over a month. So a time column might have a value 168 hours to represent 1 week interval, or a value minus 48 hours and 30 minutes to represent a time 48 and a half hours ago. The full format is thus plus or minus, and 3 digits for hour, then minutes and seconds. The 840-hour limit, by the way, stems from arcane internal details regarding how the time columns are stored. Finally, we have the SQL standard timestamp column. Now, this records a date and a time, like datetime, and uses the same format. So, why does SQL have yet another type for this? Because of time zones. Timestamp and datetime both record an absolute time by counting to microsecond accuracy from a starting time, or epoch, which is January 1st, 1970. And they both use GMT or UTC as their reference time zone. But timestamp displays data in whatever the current time zone is, translating from UTC. And it lets the user express values for comparison or setting of the column in the local time zone. Datetime does neither. All interactions with the datetime column must be in UTC time. The distinction is important in any database that's backing a web application, by the way, which in principle can have simultaneous users in every time zone of the world at once.